get started. Our first speaker is Yosuke Sumitomo, who will be telling us about a stringy mechanism for a small block.
Thanks. I'm talking about this title, and this is based on the paper was Henry Dye, and also something more. So let's start. So the motivation is a stringy random scale. This is because there are so many types of the vacuum in string theory which we can consider as a result of actually a variety of the complication, including the Calabi-Yau. But today we just focus on a class of Calabi-Yau, which is given as a species type of the volume, as like this form, or as like in today's morning session. For example, in this framework, we can say, for example, let's see, following the last paper, the one P11169 include the 2 Kara moduli and the 272 complex structure moduli. Or on the other hand, the F11 has a 3 Kara, while the 111, the complex structure moduli, or also something else. Also, there even in today's morning session, there are so many variety of the model can be considered in the switches type of the framework. But the key point here today is actually all of the model can be stabilized in the presence of the non-perturbative term and also some other term, but quite non-trivially. So the question here is there actually any implication of the multiplication of these kind of the vacuum? So let's start. So before they're doing this somewhat in detail, let me simply give you some key point of this talk. The key point is actually the so-called product distribution. This product distribution, for example, if we assume this z parameter, which is given as the product of the random parameter as y1 times y2 times y3 or something like that, then the distribution, and also let's assume that, for example, the uniform distribution for each variable. Then the product of this distribution gives us a sharp uptick towards this z equals 0 region. And once we multiply the one word, let's say 3, then we also saw the much more sharp uptick in this problem. And the same is true for normal or Gaussian distribution here. So then, but we today introduce this mechanism to apply the actually cosmological constant. But there are some concerns about the presence of the many terms appearing in the string potential. But even in the presence of the many terms, because string complication requires all terms are actually correlating each other through the stabilization dynamics. And that gives us finally maybe this kind of form, so that we have some coefficient which is product given as a product of the random variables, and also some function here. But we finally see that this z actually has still peaked around this 0 region. This is a key point in this talk. But unfortunately, even though we have the sharp uptick in the distribution, the suppression regarding this sharp uptick is actually not so strong. Actually, that's quite mild for our current CC. That's the story of this talk. So let's keep going. And let me introduce our working model, which is given in the type 2B, which I'm currently going. And following and we are working actually in the Dojita space. So we made some mechanism for the mass matrix actually. Otherwise, all of the mass matrix suggests a Gaussianly suppressed probability for such a Dojita vector. So we are not likely to meet. But however, if there is a hierarchical structure in the mass matrix or the potential, then actually that helps the stabilization moduli at positive cosmological constant quite hugely. So let's work on 2B. And in 2B, fortunately, we have a no-scale structure. And the no-scale structure divides the structure for Kara and the complex quite nicely. And this is quite helpful. So we use this. And in this framework, for example, the complex structure and the Dirac moduli are stabilized by fluxes, we can say. And also the other corrections, including a non-perturbative effect and the alpha prime correction, and also some of the localized prime can contribute the stabilization for the Kara module. So we may divide the potential in this way, and the first term contribute stabilize the complex module at high energy scale, while the other remaining terms stabilize the Kara module at slightly bit lower scale. So we can separate these two things. And today we just focus on the Kara part. assuming their complex part or complex moduli are all stabilized. So from now on, we use this model. Kera includes the alpha prime collection here, and their volume is given as a switch form, and also we added a non-particle term in the superpotential here. So this is our model in Mali, and we further simplify the model by expand or using their perturbations in terms of this non-particle effect and also their large volume suppression, so that we keep at the next reading order up to these terms. And we actually neglected the second reading order with respect to this perturbative expander, but this is okay because our interest is for small cosmological constant. And actually, this first term dominates in this other cosmological constant analysis that we will see a bit later. So, assuming these things, and also let me simplify the potential just restricted in one Kera module, and also real part of it, because the imaginary part is rather trivial because it's given with oscillational potential, so that we can easily find the minimum of it. So let's focus on just the real part. And then the potential finally simplified to be this form, just two terms in it. And the C is just a combination of the coefficients, and then this Xi is the Kera moduli combined with some coefficients here. And then consider the stabilization of this potential actually resurrects the parameter of this C to be some certain region given like this. This will be explained by the Marcus talks maybe a couple hours later. So I'm not going in detail, but the important thing is the C is restricted in some certain region. The lower bound is given as just a positivity of the potential, while the upper bound is given by the positivity of the mass square in this case. And but since we are interested in just a small CC region, so we further focusing on the C approximated to be just a lower bound. So we finally simplified potential to this form. And this is quite simple because this is just a combination of just some coefficient like W naught and A1 and the large A1 or gamma 1 or C or something like that. And this figure just illustrates how this bracket part behaves. So we can easily find the stable vector at positive, stable vector at positive CC. So let me rewrite this potential to just simplify. So rewriting this potential by redefining each coefficient, but I simply neglect these three coefficients just right now. But if we simplify this potential, we finally reach this simple form of the lambda. And then we further analyze how this behaves. So now, let me import the randomness of the simplified potential. So because this W1 and the W2 are roughly given by the W0 and the A1, and this W0 and the A1 are given after the stabilization of the complex moduli. So especially the stabilization of the complex moduli is given quite non-trivial way, so that we can say in one way the W0 is 1, but while the other way W0 is 0.5 or something else. So treating this kind of variety, we consider rather this W1 and the W2 parameter as a random variable here. So just for simplicity, let's assume that this W1 and W2 random parameter obeys a uniform distribution from the 0 to 1, just for simplicity, and then analyze what is happening in this random. And the probability distribution of this random currently quite simplified, so that we can calculate the probability of the distribution function of random by analytically, actually. The formula for the probability, let me call this as a PDF. The PDF is given by just integrating over the two constraints. The one constraint is for the definition of random, but the other constraint is for the definition of the C parameter. And they're also integrating over the validity range for the C parameter. Then we can get the PDF for the random. So let's calculate. But before doing the full analysis, let me just state the key fact of this product calculation, product distribution. So if we just neglect a constant part, the C, then this lambda is, or let's define the Z. If the Z is defined as just a product of the random variables, then we can calculate this probability distribution function of this random variables. And we can perform this delta function quite easily. And finally, we got this form. And this form suggests once we reach Z equals 0 region, then there is a clear divergence in this function. This is the interesting feature of the product of the distribution. But we have some more constraint with the C parameter. Then what happened is we can perform the integral I showed in the previous slide, but the still result is not changed. So still we have a divergence when we reach the lambda equals 0 region. And this, we can compare this result with actually the numerical simulation, which is obtained just analyzing or solving the moduli field by giving a random parameter of W0 and A1 without any approximation, meaning approximation for the even perturbation and also approximation for this linearization. Yeah, I took here. So just I analyze the full potential numerically, and we saw the nice agreement here. This solid curve, such as just given by this analytic formula, but this histogram is given by the numerical simulation. And actually, once we reach to a small lambda region, then this plot may be better. This is a log plot, log histogram. But then once we reach to a smaller lambda region, then this analytical result perfectly agree with the numerical simulation, even without any approximation. So now, I just simply reaching the end time. So I'm simply assume the zeroness of the, I just simply include the zeroness of the W0 and A1, but this is quite natural in Stringy setup. Let me just briefly explain. For example, in the T6 model, we can write down this way, and then we can stabilize the moduli of this compressed and dilaton at supersymmetric vacuum, so that we finally get this expression. This is, for example, the Riemann-Basler analysis. And we can say that, let's say, that if this combination of du is reaching 0, or otherwise this s is reaching 1, each are the real part of each moduli, then we see easily that the W0 is easily reaching to be 0. On the other hand, the same is true for A1. In A1, we have a non-trivial configuration in the presence of the break position moduli. That is given as x1. But this x1 dependence appearing here is given as this form. And once we hit, for example, once this display position hits the position of the descent plane, that means that this f of xi is equal to 0, so that we can easily see the zeroness of the A1 is sub 2. So this is just for the analysis for single moduli. So let's proceed to the what happened in multiple case. In multiple case, as I said, once we multiply the random variable, then we saw there's some clear sharp, the much sharper behavior in the distribution function. Actually, analytically, we use this formula once we assume uniform distribution. And if we calculate the expectation value for this, then actually this expectation value for this W is exponentially surplus. So this would be helpful to get a smaller CC in some sense. And since this W and A1 are actually given other complicated function of the complex structure or the dilaton moduli, so that it is possible that this W0 or A1 itself has some sharp bit in its own because of this random product of the random variables. But that's a fact appearing in coefficient. Sure. So then what happened in the next part, that's the bracket part. And this requires some dynamics to summarize the Kähler moduli. And let me briefly, because I don't have the time. So this is the potential, assuming the perturbative rates, and consider the multiple Kähler. And what happened here is that once we increase the number of the Kähler, then actually we saw the much sharper peak. This is the outcome of the correlation of each potential. And once we can increase their moduli number up to 6 currently, and we solve this kind of behavior. But this suppression is actually mild because backup efficient in the exponent is not so big, so that even if we have, let's say, 10,000 Kera moduli, we didn't see their agreement with the current cosmological constant. So, but this is clearly suppressing. And there is another problem, actually, in this framework. This suppression also works for the moduli mass. And I just simply show the result. And the moduli mass is also suppressed. But the point is that this is suppressed quite larger compared to the Kera moduli and the cosmological constant. Sorry. And this just shows the tendency that the mass square, the expectation value of the mass square is suppressing much hugely compared to the expectation value of the lambda itself. So, let me summarize. So today I introduce a Stringy random. Today I use the mechanism of the Stringy random landscape to make the CC small, and that is done by the two things. One is the product distribution. The other is the correlation given by the dynamics. And actually both works for making the CC small. But currently I have a potential problem to deal with to reach this smaller current or cosmological constant because of the modular problem. So that's it. Thank you.
Sorry. Next is. Thanks. Okay, so I better start now, I think, with Nobuyoshi. So is there any question for Yosuke while Nobuyoshi is setting up his slide?
So how can you estimate if I got correctly, you were getting the cosmological constant suppressed, but not that much suppressed?
Not that much.
But you say that with increasing the moduli, it will be further suppressed. How can you estimate that without doing the calculations?
You mean analytically?
Yes, I mean, because we have to know the shape of the potential and those things.
Yeah, I just simply assume the presence of the non-particle effect to subtract the Kera potential. And of course, there are some other mechanisms where I just neglect currently the other alpha prime correction. Other than alpha prime correction, I added in the Kera potential. So it may be possible that the story will be changed in the presence of the other correction. But within this framework, at least I clearly saw that the decrease of the cosmological constant itself as increasing of the number of the Kera moduli.